Welcome to section 2.5. In this section, we're going to be looking at some properties and formulas for derivatives of many different functions. In the previous sections, we have looked at the foundation of the derivative, how we define it using its limit definition. But now we can start looking at faster, more efficient ways of calculating derivatives, bearing in mind that all of these formulas that we're going to develop here do have a basis in that limit form of the definition. But once we have these tools, we can start using them to great effect. So to start off, we're just going to start listing off a bunch of different derivative rules that we might need, and we're going to draw a bunch of examples using them. So first thing to talk about are two different notations that we use to express the derivative of a function f of x. So we have our standard f prime of x, that prime notation, which you could also just write like as y prime if you have a function y equals f of x. The alternative notation that we'll use also pretty frequently is what we call the Leibniz notation. This notation is written dy dx like this. Dy dx, so this is read as the derivative of y with respect to x. Okay, just like this one, right, is the derivative of f with respect to x in the function here. So these both mean the same thing. They're used interchangeably. You can see them used in different contexts, and some might be more useful than others, just depends on what's going on. You could also rewrite this as like derivative with respect to x of f of x, something like that. Okay, like this notation is also equivalent to f prime of x. So we'll see these notations popping up throughout our conversation on derivatives. So now, a few derivative rules that we're going to be able to use. If the function we're working with is a constant, f of x equals c, then the derivative of a constant function is going to be 0. The reason for this, if you think about derivative represents, right, the slope of the tangent, it's that rate of change. If you picture a constant function, that's a perfectly flat horizontal function, right? So if you find the tangent at any point, the slope is going to be flat, right? The slope is going to be 0. And that's where we get that idea from. One of the most important rules that we're going to be using here is the power rule. The power rule says if you have a power function, x to the k, where k is a constant, the derivative of this power function, you bring down the k, and then you take k minus 1 up in the power. So derivative of x to the k is k times x to the k minus 1. So you bring down the k, subtract 1 from the power. We can also differentiate exponential functions like the e to the x, the natural exponential function. We will work with this one a lot, more so than other exponential functions, because its derivative is actually also e to the x. So it turns out that the natural exponential function e to the x is its own derivative, and that makes it really handy for calculations. So we'll see that one popping up a lot, especially when compared to other exponential functions. If you have a constant multiple, so if you're taking the derivative of a function times a constant, you can pull the constant out of the derivative. So if you take the derivative of k times f, that's the same thing as k times the derivative of f. So again, we can pull constants out of those. And if you're taking the derivative of a sum or difference, so of two different functions being added or subtracted together, that is equivalent to taking their derivatives separately and then adding or subtracting them together. Okay? In other words, you don't have to find their derivative collectively at the same time. You can just find these derivatives individually, separately, and then just add or subtract the results together. Now, these are just some of the derivative properties. A lot of the others come from properties like this. And so we'll see kind of how those go in practice as well. Now, when it comes to higher order derivatives, when you take the derivative of a function, you create a new function. That new function is also potentially differentiable. So you can take the derivative of a derivative function. This is what we call higher order derivatives. So for example, if you wanted to take the derivative of the derivative, so that's y prime, to take its derivative, it becomes y double prime, okay, or f double prime of x. With the Leibniz notation, the dy dx, basically it looks like this. So this will be d squared y dx squared. That's the second, this is all the second derivative. So f double prime of x, or d squared y over dx squared. That would be the derivative of the derivative. Okay, we can take, the third derivative, so that's f triple prime of x, or d cubed y over dx cubed. And this process continues. You can take as many derivatives as are necessary, but there is one thing to note. Once you pass the third derivative and you move on to the fourth derivative or higher, it doesn't really serve us to be putting prime notation here. Like, what if you wanted the 10th derivative? Then you're going to have to do like this, and that's not a helpful notation. So we don't do that. Once you hit the fourth derivative or higher, we start using this parentheses notation. So I know this looks like f to the fourth power of x, but it's actually the fourth derivative of f of x. Okay, so the parentheses are a very important distinction, because without the parentheses, it is the fourth power. But with the parentheses, it is the fourth derivative. Now, the one notation that does not change, that stays consistent, is the Leibniz notation. The Leibniz notation, it just keeps counting up no matter what. And if we were to keep this going, this could work for as many derivatives as we want. So we have the nth derivative here. We can take as many as we want. And just keep applying the same derivative rules and properties to them. So let's try some examples out here. Find the derivative of y equals 5x squared minus 2.1x. So we can utilize a couple properties here. So we can split this up across addition and subtraction. So a derivative of 5x squared minus derivative of 2.1x. We can pull constant multiples out of derivatives. So then for this first one, we would get 5 times derivative of x squared. So you bring down the 2. So that's 2x to the 2 minus 1. So that's 2x to the first. Minus 2.1. Derivative of x. This one is a little bit different, but if you think about it in terms of the power rule, this is x to the first. So if we bring down the 1, there's a 1. Subtract 1, we get x to the 0. X to the 0 is just 1. So this actually gives us kind of a nice derivative rule here. Derivative of x is just 1. So you might save that one because that'll come up pretty frequently. So we get this. So that's 10x minus 2.1 is the derivative of that function. Right? For something like number 2 here, so again, we can pull constants out and we can split up across addition and subtraction. So we get 5 times derivative of x squared is 2x to the first again, minus 7 times derivative of an x is 1, plus derivative of a constant. Remember, our derivative of a constant is 0. And I should say that's a derivative of a constant by itself is 0. That was what this first property said up here. If you take the derivative of a constant by itself, it's 0. If you have a constant multiplied by the function, so a constant multiple, those ones just tag along as we take the derivative. So like these ones, the 5 and then 7. They just tag along with the derivatives here. But because the 9 is by itself, its derivative is 0. So that gives us 10x minus 7. And that is the derivative of that function. So let's look at some different functions here. Differentiate y equals negative 6 times radical x. So when it comes to evaluating radical functions, we have to bear in mind that a radical function is the same thing as a fractional power. So like the square root of x is the same thing as x to the 1/2. So if we want, I'll use the Leibniz notation here. Pull out the negative 6, derivative of x to the 1/2. So if we take x to the 1/2, so we're going to bring down the 1/2 and subtract 1. So that's 1/2 x to the negative 1/2. Then we take this negative power, so we want to move it down to the bottom. So that's going to be 1 over 2x to the positive 1/2. Right? Negative power became a positive when we moved it to the denominator. And x to the 1/2 here is just radical x again. So negative 6 times 1 over 2 rad x. So it's negative 3 over radical x is the final version of that. So this is also a good one to know. So derivative of the square root of x is 1 over 2 rad x. It's a good one to have in our toolkit. And you can always derive it using the power rule. For this next one, we have y equals 3 over x minus x over 2. So derivative, the 3 is immaterial. We can keep the 3 out if we want. Taking the 1 over x here, that's the same thing as x to the negative first. So you can see a pattern here where we're turning all of these functions into standard power functions. And then minus the 1/2 can come out, or it can stay in, either way, times x. Now, when it comes to taking the derivative of x to the negative first, we're going to bring down the negative 1 and subtract 1 here. So be very careful when dealing with negative powers, because that's going to be x to the negative 2 now when you subtract 1. So it's not 0 because it wasn't positive 1. So it keeps going more negative as we go here. minus 1/2. Derivative of x is 1. And for our final answer, we need to move this back down into the bottom again. So that's going to be 3 times negative 1 over x squared minus 1/2. So we get negative 3 over x squared minus 1/2. Okay, so functions with x in the denominator like this, functions with radicals, these are all cases where the power rule can be used, even if it's not quite as obvious at first. For one like problem 5, so if we want to find s prime of t and s double prime of t, so we go one derivative at a time. Derivative of 196 by itself is just a 0, minus 16t squared. So derivative of t squared, we bring down the 2 and subtract 1. So we're going to combine 16 times 2 is 32, t to the first. Okay, so that's just negative 32t is the first derivative. And the second derivative is the derivative of that, which is just negative 32 times 1. So just negative 32. If, for example, the question had asked for the third derivative, we would take the derivative of this, which would just be 0. And then we would just have zeros the rest of the way out. Right. Let's try a couple more. So find f prime of x for these following functions. So the key here is we need to rewrite these functions in proper form to be able to use something like the power rule. So f of x, so we have negative 3. This is x cubed, and we're taking the 5th root of it. So that's the same thing as the 1/5 power. So this is x to the 1/5 and cubed, so that's x to the 3/5. So f prime, we have negative 3. We're going to bring down the 3/5 to the front, and then subtract 1. Which in terms of this fraction really means we're subtracting 5 over 5. Right? So 3/5 minus 5/5, so that's x to the negative 2/5. And then when you have a negative power like this, we need to move this object back down to the denominator so that we can keep its positive power. So we get negative, I'll go ahead and combine these right now. So that's negative 9 over 5 x to the 2/5. And then the problem gave it to us in terms of the radical notation. So let's go ahead and put it back in the radical notation. So it's negative 9 over 5 times the 5th root of x squared. So that would be our final version of the derivative, put back into a similar notation like the original function was given. For one like the second one here, so we have another rational function. So let's rewrite this. We have 2x to the negative 2. So to get f prime, we're going to bring down the negative 2. So it's 2 times negative 2x, and we're going to subtract 1. So it's going to be negative 3. So we get a negative 4 over x cubed. And for this third one, we have a rational and an x in a denominator, so we can go ahead and take both of those into account. So this is going to be 2. It would be x to the 1/2, but because it's in the denominator, it's x to the negative 1/2. So we bring down the negative 1/2, and we subtract 1 from that. So that's like, again, subtracting 2 over 2. So that's negative 3 over 2. 2 and 1/2 will cancel. The negative's still there, though. So we get negative 1 over x to the 3/2. Or back in radical form, negative 1 over the square root of x cubed. Okay, so there are all kinds of functions that we can differentiate, all different types of combinations of functions that we can differentiate. So there's lots and lots of extra practice that we can get. And you can even try just making up your own functions and try applying these properties, these rules to them. But all sorts of different variations on these same rules that we can encounter. So for the next set of examples, so we're going to skip over these couple, but we're going to look at example 4 here. So this says, find the points on the curve where the tangent line is horizontal. If such a point does not exist, state that fact. So when we say the tangent line is horizontal, we're saying that the tangent line has a slope of 0. Right? That's what it means to be horizontal. It means to have a slope of 0. But another word for slope is derivative. So really what this question is doing is it's saying find any points on these curves where the derivative is 0. Okay, so instead of saying tangent line is horizontal, we're saying where the derivative is 0. So first we take the derivative. So like for this one, power rule, we bring down the 2. The 2 cancels with the 1/2. So this is just x minus 0. Derivative of 1 is 0. We're going to take this result and set it equal to 0. So the only point where the derivative is 0 is at x equals 0. So let's find the y value, the output. That's going to be 1/2 0 squared minus 1. So that's just negative 1. So at the point 0, negative 1, this curve, this parabolic curve, has a horizontal tangent line. Okay, and that's actually the vertex of that one, so that's like down here. That's where the horizontal tangent would be. For this next one, take the derivative of this polynomial. So bring down the 3, that's 6x squared. Bring down the 2, that's 6x. And 12 times 1. And then derivative of 1 by itself is 0. Set that equal to 0. Let's go ahead and divide everything here by 6. Simplify this a little bit. So x squared plus x minus 2 equals 0. This is factorable as x plus 2 and x minus 1. So we get x is negative 2 and x is 1. And then find the points that correspond to those. So f of negative 2, which I'll just tell you is 5, and f of 1 is negative 6. So there's 2 points. So there's negative 2, 5, and 1, negative 6, where this function has a tangent line that is horizontal, or in other words, has a slope that is 0. Then for one like part C, f prime of x equals 3 times 1 and then minus 0, so just 3. If we set that equal to 0, clearly 3 is not equal to 0 and never will be equal to 0. So this one, there is no horizontal tangent line. So it does not exist on this one. The reason that that's the case is because this is the equation of a line. So this is a line in slope-intercept form, right? mx plus b. So this is a line that hits the y-axis at -1 and has a slope of 3. So this line is always growing like this. It never levels off and goes flat. It never has a slope of 0. It never goes horizontal. That's why the derivative will never be equal to 0, algebraically. Right. Then let's look at one last example here, throw a little bit of context into this. If a rock is thrown from the ground with an initial velocity of 80 feet per second, then the height of the rock in feet at t seconds can be modeled by s of t equals negative 16t squared plus 80t, with t going from 0 to 5. Find v of t and a of t. So this is asking for velocity and acceleration. So for velocity, this is the rate of change of the rock's position. So in other words, when we say rate of change, we're talking about a derivative. So that's v of t is going to be s prime of t. So we take the derivative, so we bring down the 2, so that's negative 32t, and then plus 80 times 1, so just plus 80. So this is the velocity formula. A of t is acceleration. Acceleration represents the rate of change of the velocity. It tells you how much your velocity is speeding up or slowing down. So acceleration is the derivative of velocity, or in other words, the second derivative of position. So it's the derivative of this, which is negative 32 times 1 plus 0, so just negative 32. When it says find v of 3, we just need to substitute in 3, so negative 32 times 3 plus 80, that's negative 16. What does this quantity represent? Well, this is a velocity at time 3, so this is in units are feet per second at 3 seconds. So after 3 seconds, when the object has been thrown, it has a velocity of negative 16 feet per second. So in other words, it's coming back down at 16 feet per second. At 3 seconds, the rock rising up or falling down? So that was kind of what we were just talking about here. So because velocity is negative, so because v of 3 is negative, it is falling down. Because if it gets thrown up, positive velocity would push it forward like this and up, but then coming back down, now the velocity is negative, it's coming back down to Earth again. At what time does the rock reach the highest height? And what is that height? Well, if you think about the object being thrown like this, the highest height is right up here at the apex, at the peak. that point is where the graph levels out again, right? It's at the top of this parabolic arc. Now, if you think back to the example we just did, this would be where the slope of the tangent, or the derivative, is 0. So, and if you think it in terms of velocity, right? Velocity is positive here, it's negative here. It had to hit 0 somewhere in between, right? There's this one moment in time where it had to stop before it starts coming back down again. So this is where v of t, which again is s prime of t, negative 32t plus 80, we set that equal to 0. So solve this for t, and we get, that ends up being t equals 5/2, or 2.5 seconds. That's how long it takes. That's the time at which it reaches its highest height. And then what is that height? Well, we'll plug this back into the position function. So s of 2.5. And so that's plugging back into this one, this original one, which I'll just tell you what we get. We end up getting 100. So the highest height that the object hits is 100 feet high, and it hits that after 2.5 seconds have passed. So the velocity up to 2.5 seconds has been positive, going up. At 2.5 seconds, it hits that peak at 100 feet high where it stops. And then everything after 2.5 seconds, like we saw here at 3 seconds, has a negative velocity because it's coming back down again. So then, what is the acceleration of the rock when it reaches the highest height? So at 2.5 seconds. So basically, we just take a and plug in 2.5. But the function for a, we saw back up here, is just negative 32. If there is no variable for us to substitute into, then it doesn't matter what this number is. It's just always going to be negative 32. And that's in feet per second squared. And the reason that we seem to have constant acceleration or deceleration in this case, because you're throwing an object upward, so it could be deduced that this is the effect of gravity, right? So no matter how hard you throw it, eventually it's going to level off, and then gravity is going to push it back down, and it's pushing at this constant acceleration of 32 feet per second back towards the Earth. That's why it's negative, if we're considering throwing it upward as being positive direction. All right, and that brings us to the end of section 2.5. So as we continue through the chapter, we're going to look at some more derivative rules, derivative properties that help us work with all different types of functions. But this has been our introduction into derivative properties.